Hello everyone, Dr. Shane back again with another Chemistry 105 lab video. We had a couple weeks of dry labs where we were balancing equations and writing formulas, and we'll have, I think, one more dry lab, but our last few labs are actual ones. So we are on, if I can get this here, it's lab 8. We'll put this up on D2L, obviously, and you should have this printed out ready to go by now. Oxidation-reduction and acid-base reactions. So I'm just going to kind of go through, and you can put a couple notes on your printout. We're not going to use the color indicator, probably. We'll probably just use pH paper again, like we did for that one activity on representative elements. I think we had to measure the pH of a bunch of stuff. And then I'm going to do some stuff. There's one procedure for oxidation and reduction, and then there are 4 procedures for acids and bases. So yeah, there's oxidation reduction. I'm going to do one of those with you now, kind of in a slightly different way. And procedure 1 I'm going to do as a demo here right at the beginning. It just takes too much time to let the reaction sit there. That's fine, so I'll do that as a demo and I'll talk about that. Procedure number 2, it tells you to take 10 drops of those different solutions. I don't know if you've done the 0.1 m. That's called molarity, moles per liter. The point there is all of those solutions have the same concentration, but they're different acids and bases, and your job will be to figure out what makes them different. And instead of doing this, it'll be a lot faster if you just tear off little pieces of pH paper and put them on a piece of paper towel, and then drip some of the different solutions on there, and then match up the color to tell how strong of an acid or base it is. But I'm getting ahead of myself. Oh yeah, by the way, a lot of this stuff, if you read through the whole experiment, you can do some of this stuff ahead of time. You can actually write out balanced equations and things like that, because we're going to talk about that. So this is a little bit of a scavenger hunt today, so see how much of this you can get done before you actually come to lab. So that's procedure 2. Procedure 3. Procedure 3 takes a little while because you're adding a few drops, measuring the pH, adding a few drops, measuring the pH. That center column there where it says color, that's if we use the solution, the universal indicator. We probably will skip that. So what I might do, I'm not sure how long this is going to take. I may have half the class do the HCl and the other half of the class do the acetic acid, and we'll just trade data. And the last procedure, it's kind of reinforces earlier things that you do. It's something I'm going to do as a demo. So we may or may not do that. So TBA is to be announced. So we may do that as a demo in class, or if we have time. I don't want to take away all the fun. And then everything else after that is our questions. So there's a whole bunch of follow-up questions for each of these parts. And actually, during my little pre-lab lesson here, there's a bunch of these you can fill out when we get to them. So try to fill out some of these answers before you come to lab, and we'll be very efficient about the use of time. And I'm going to refer to some of this stuff as we're going. Just have this handy, ready to go. Okay, let's get started. And for this one, I'm definitely going to be wearing some goggles, and I'm going to be bouncing around a little bit in the procedure. So I'm not just going to go one to the other because of time. So the first one I'm going to do is under acid-base reactions on page 2, procedure number 1. And I'm doing this as a demo. And I'll describe what's happening. And you can write it down, I guess. And then we'll talk about what happened. I want to make sure that the camera is centered properly. I don't think I checked that before we got started, so sorry for my amateur production. Okay, good. We're good to go. And then I'm going to do a little mini lecture on all this stuff. You don't have to worry about all this now. You can copy it down now if you want to, but yeah, just sort of leave that there, and I might add some things to it. So this is, again, acid-base, procedure 1, page 2 at the top. It says combine 2 drops of 6M HCl and 2 drops of 6M NaOH. Again, the M, don't know how far you are in lecture, stands for molarity. It's moles per liter, and that doesn't make any sense to you. It's a unit of concentration. And I have two solutions here. Here's HCl and here's NaOH. They're not exactly the concentrations written here, but it'll make the point. So what we're going to do is put a little bit of each. Now these are very concentrated. So these are actually pretty dangerous solutions to handle in the lab. But I'm just going to do small amounts. So I've got a disposable pipette for each. And I'm just going to put a few drops of each, I don't know, 5 or 6, less than 10, here in the middle of this watch glass. You won't see much happen right away. And in the procedure it says, add a couple drops and just let it sit there. Well, you're letting it sit there so that the water evaporates. And all you're left behind is something, or nothing. I don't know, we'll wait and see. I'm going to accelerate that by putting it on a hot plate. This hot plate that I have over here is already pretty hot. So we'll see how this works. And there's a little bit of a crack in this watch glass, but I think we'll be okay. It's Pyrex, which is meant to withstand high temperatures. Okay, anyway, so I'm going to add some HCl, and the bottom of this watch glass has been sitting out, it's room temperature. So I'm just going to take several drops of HCl. It's a clear, colorless liquid. The NaOH is also a clear, colorless liquid. And you're not going to see anything like fancy happen here, like colors or anything like that. But I don't know if you can see it. I can see a little bit of this. I don't think you can see it. A little bit of water vapor actually came off when I added these two together. What does that mean? This is a pretty exothermic reaction. The bottom of the watch glass is very warm. It's much warmer than it was. So that's actually something from the last acid-base reaction. We're going to measure how high the temperature goes. So observations you can write down here. Take my word for it. A little bit of water vapor came off, and the reaction gave off heat, which is exothermic. So we've got the two mixed together, and now I'm going to put them on the watch glass. Hopefully that won't crack. If it does, I'll probably just jump a little bit, but it's not gonna, I'm gonna keep my goggles on. Okay, so we have to come back to this one. And I'll refer to this reaction because it's HCl plus NaOH. So it's an acid-base neutralization reaction, which I think you already know how to handle. Okay, like I said, I've got acids and bases up here. I'm gonna leave my goggles on for this lesson. Okay, now I'm gonna go back to the very beginning of this. So we're looking at two different kinds of chemical reactions here, and I think you did classification of chemical reactions in lecture. We've already done double replacement when we did the precipitation reactions one, where the ions just trade places and we figure out a precipitate form. That's one type. You probably talked about combustion reactions, which is something reacting with oxygen. Well, it's usually something that has carbon and hydrogen and sometimes oxygen and other things. And you're producing, if it's just carbon and hydrogen combusting, carbon dioxide and water, which is called complete combustion. So we're looking at two other kinds of reactions today. Okay, so just briefly, I'm not going to replace Dr. McCann's lecture, or if you're using this in another semester, whoever's lecturing for you. So oxidation reduction is sometimes called redox. It's just an abbreviation that makes it sounds like it rolls rhythmic rather than ox-red, redox. And basically what's happening here is you have one reaction that's giving up electrons and another reaction that is taking those same electrons. And there's a nice mnemonic device here. I don't know how well you can see this. The mnemonic device is oil rig. Oxidation is losing electrons. Reduction is gaining electrons. So oil rig. Another one, if you've had chemistry before, is LEOGR, L-E-O-G-R. Loss of electrons is oxidation. Gain of electrons is reduction. Loss of electrons is oxidation. Gain of electrons is reduction. And actually I see our little reaction over here is done, so I'm going to turn off the heat. And I'm going to come back to that. It's already finished. So use whatever mnemonic device makes sense to you, oil rig or LEOGR. And I'm going to use two examples, one not from the lab and one from the lab in a different format. Okay, so actually I think we're safe now that the heat is off there. Good, I can take these off. So here's an example. Iron, or iron and steel. So iron atoms, however they're available. Steel is a combination of lots of different things. So iron, as you know, rusts. Okay, other kinds of metals rust, but iron is the main one. Rust is actually a very complicated mixture of different things. Well, it's not that complicated, but here's one chemical reaction for rust. Iron metal, so that'd be Fe, just elemental iron, solid, reacts with oxygen in the air, and this is not combustion, by the way. Not combustion. And it forms, and you can name that compound. If you want to stop the video briefly and name this compound, what would you call that? Well, you can stop it if you want to. This would be iron, Roman numeral 2, oxide, iron 2 oxide. So here's what's happening. Iron starts out and it doesn't have a charge. Old chemistry textbooks would actually put 0 when there was no charge. Most chemistry textbooks now don't do that, they just leave it. So iron has no charge here. Oxygen also doesn't have a charge. It's not ionic, so it doesn't really make sense to talk about charge. But over here, oxygen has a -2 charge, and iron has a +2 charge. This is an ionic compound. So what we have happening here, if you want to think about this like two different reactions, this is exactly what it is. One's oxidation, one's reduction. We have iron going to iron +2. And we have oxygen. Actually, you know what? If you want to, we don't have to do this now, but this is not balanced. So if we wanted to balance this, we'd have to put a 2 there and a 2 there. So it's 2 irons becoming 2 iron 2 plus. Again, this example doesn't make sense. I'm just using this for illustration purposes. And we have 2 oxygen, -2 ions here. Okay, so that's fine. So iron is going from 0 to +2. Oxygen is going from 0 to -2. And it's just happening twice because of the balanced equation. So don't get hung up on that. So I'm just kind of curious. One of these reactions is oxidation. One of them is reduction. Which one do you think it might be? If you're going from 0 to positive charge, what's going on there? How does something gain a positive charge? It loses electrons. And what's left behind are more protons, so it's a positive charge. So iron actually loses 2 electrons, but it happens twice. So we're actually losing 4 electrons here, 2 for each iron. And again, that's maybe more complicated than it needs to be. And when we say that you're losing electrons, they're written as a product. So this is actually oxidation. Iron is losing electrons to go from 0 to +2. It's losing electrons. Well, the only choice for oxygen is that it must be gaining electrons. It's going from 0 to -, so it's gaining electrons. It's actually gaining 2 electrons, and that's happening twice. So oxygen is gaining 4 electrons. I don't want to get hung up on that. So you lose electrons, you gain electrons. And that's one example. Great. The example I want to show you is a version of what's in here. There's only one set of oxidation-reduction reactions. There's 2 reactions you're observing. The second one I'm going to let you do on your own. So, reaction number 1 says, add 1 piece of zinc metal, so Zn solid, you'll have little vials of that, and add enough copper 2 sulfate solution to cover the zinc. So this is the copper 2 sulfate solution from the metathesis, so you'll just add it until you cover the zinc and observe what happens. I'm going to do this a little bit differently. I don't know, this is kind of cool. So, I don't know if you know about pennies. In 1982, I think, pennies went from being solid copper to a copper-coated penny with basically scrap metal on the inside. A lot of that scrap metal on the inside is actually zinc. And I don't know if you can see it from here, So this is a penny from 2013 that we cut in half, which is legal as long as I don't try to glue it back together and use it as currency. Plus, I think there's a push to get rid of pennies. So I just need to show you this because I don't know if you can see it from way back there. And maybe your high school science teacher showed you this. So there's a copper penny, and then the metal on the inside is a combination of basically scrap metal, but it's essentially zinc. So I'm gonna take some copper sulfate and drip it on, well, one of these and leave the other one alone. And we're gonna see what happens. And then I'll erase this and write this as another example. So what I'm doing here, what's the chemical reaction? Let's assume that all this exposed silver-ish looking metal, it's not silver, is zinc. It's a mixture of metals, but for now, we're not gonna worry about that. So it's Zn solid. So we'll write Zn solid as the reaction. Well, what are we reacting it with? Well, we're reacting it with copper sulfate, but you have to take my word for something. The sulfate is a spectator ion, it doesn't react. It's copper 2 sulfate, excuse me. So this is actually reacting, if it does react, with copper plus 2 ions. And I'm just gonna touch, there we go. That worked really well, actually. Yeah, that worked really well. So, it's hard to do this with my goggles on. Okay, so here's the after. So here's the one I reacted. I dripped the copper sulfate on it. It kind of made it dark. And this is just the other half that I didn't do anything to. So something reacted here. It's not just wet, and I didn't burn anything, so it's not like I put soot on there. So what actually happened? Well, what actually happened was copper metal formed on the surface of the zinc. It went from copper plus 2 ions in the solution of blue copper 2 sulfate to solid copper metal. This is what's called electroplating. It's not exactly how it's done commercially, but we're coating one metal with another metal. It's called electroplating. So how will we write the chemical reaction for all this stuff? Okay, and you'll see this in lab a little bit more precisely than this. I just thought this is cool with the pennies. All right, let me write out what's going on here. So this is reaction 1. So let's try to stay organized here. It was kind of a pain to cut that penny in half, by the way. So this is reaction 1. Well, the thing that's happening, you're taking zinc metal, the exposed metal in the penny, and again, take my word for it, you're reacting this with the copper plus 2 ions that are there in solution. It's copper 2 sulfate pentahydrate, but that doesn't really matter. And what's actually going on there? Well, we're forming copper metal. Is what that dark substance was on the surface of the zinc. Well, the other product, so copper plus 2 is becoming copper 0. So some of the ions that were in solution are now metal, which is kind of weird. Well, if that happens, something had to happen to the zinc that was on the surface of that cut penny. Well, what happens to that is the zinc is now at the surface. It's no longer metallic zinc, but it turns into zinc plus 2 and then is dissolved in the water. So here, if you want to think about it, you've got, well, I guess we can do it this way this time. Maybe this way makes more sense. So zinc is becoming zinc plus 2. Copper plus 2 is becoming copper 0. So zinc is, what is zinc doing? Zinc is losing 2 electrons to go from 0 to plus 2. So you lose 2 electrons and you're left behind with something that's positive. So if you're losing it, that's oxidation. copper is gaining those same electrons. I didn't say that before. The electrons that are lost are the same ones that are gained. It's like an electric circuit. I didn't say that before. So copper plus 2 is gaining 2 electrons. The same electrons that are lost here. So that's reduction. So to be precise, zinc metal is oxidized to produce zinc plus 2 cations. Copper plus 2 cations are gaining 2 electrons, so they're being reduced. Copper plus 2 is reduced to form copper metal. Okay, there's a couple of questions in the, after all these procedures, that ask for the definition of oxidation, the definition of reduction. Okay, I just gave those to you. And you're asked to write a balanced equation, which metal, okay, I think you can actually do reaction 1 now completely based on what we just discussed here. But you'll do it again because it's good for you to see it. And it's not the same as this, it's a little different. Okay, so that's oxidation and reduction. It's an overview. Let's go to acid-base. Nice. So procedure 1, let's go back to what we did. It's done. It is done. This glass plate is still a little hot. Pretty sure you can see that. I'm thinking you can probably see what's on this plate right now. It looks a whole lot different than it did before, where it was 2 clear, colorless liquids put onto the plate. And then I boil off the water rather than let it evaporate. And what is that? What do you think that substance is right there? I added HCl and NaOH, acid-base neutralization. It produces water, which is now gone, and then a salt that's left over. And salt is in quotes. It's really an ionic compound. All right. Well, maybe now I'm insulting your intelligence, but let's at least talk about it a little bit. And actually, procedure number 1 for acid base and procedure number 4 are very similar. Very similar. Okay. So this is the demo. Procedure 1: combine the drums. What are your observations? There you go. What are the products of the reaction? Okay, I'm gonna come back to that. I think what I'm gonna do now is my little mini lecture about acids and bases. And I don't think we have to do too much, because you've seen most of this already, and we'll see what happens. All right, oxidation reduction is done. I just need this space. Acids and bases. You'll do much more with this in the lecture. I'm not going to talk much about the pH scale. I think we've done that. pH 7 is neutral. Perfectly pure water, very difficult to get, at 25 degrees Celsius. It has a pH of 7. Fine. If it's less than 7, it's acidic. So say it's 6, that will be weakly acidic. If it's 1, that will be strongly acidic. If you go above 7 up to 14, that's more basic. So if the pH is 8, that's weak base, weakly basic. If it's 13 or 14, that's strongly basic. So we use these words weak and strong in reference to pH, but what does that actually mean? What does that mean chemically? Just saying it's equal to a number is one thing, but here's what it means. Strong and weak are, what that means is how much do they dissociate when you put them into water? Just so you know now, concentration of molarity does not mean strength. So high concentration does not mean necessarily that something is strong or weak. Strong and weak means how much do they dissociate, break apart when they're put in water. Strong acids or bases, I'm going to do acids and maybe mention bases. Some of this you have to do on your own. They completely dissociate in water, 100%. If it's weak, you don't get much dissociation. So the examples, and I'll do acids for my example. Well, okay. HCl, hydrochloric acid, is the classic strong acid. When you put this into water, you get H plus. That's what makes something an acid, by the way, that it produces H plus in water. So I'm not going through all the definitions. What produces a base in water? OH minus, hydroxide ions. H plus, acid, OH minus base, acid-base neutralization, H plus OH makes water. Okay. So that's called dissociation. I think we've talked about that a lot this semester. But that basically happens 100%. So there's nothing that remains as a neutral molecule, HCl. It all dissociates into H plus and Cl minus. The classic weak base, which I think is, I'll just use the same symbol, HC2H3O2 aqueous. This is called acetic acid. And it's written, it's kind of funny. Students will often ask, why don't you just write C2H4O2? Well, it's written this way to indicate that this is the hydrogen that dissociates. Not all 4 hydrogens dissociate, only one of them. That's called a monoprotic. H plus is a proton, if you think about it. Okay. So it's a monoprotic acid. HCl is a monoprotic acid because there was only one. So it's only this one that breaks off, if you will, when it dissociates. But now, when this reacts, I think it actually turns out to be less than 5%. What does that mean? Less than 5% of acetic acid molecules written as a neutral molecule dissociate into ions. Well, the ions here are H plus, and then all this other stuff that's left behind with a negative charge. It's the counter anion. In this case, that's called acetate, which I believe is a polyatomic ion from your sheet that Dr. McCann gave you. So C2H3O2 negative, just it has to be. So that's what strong and weak means. So one of the things you're going to do is you're going to take the pH of a set of acids and bases that have the same concentration to control that variable, and measure the pH and then identify them as strong versus weak. So you'll measure the pH of HCl, you'll measure the pH of acetic acid, again, same concentration, and then explain what you observe with the pH paper based on these definitions. Okay, that's fine. I didn't do the same thing for bases, but I'm going to leave something up to you here, so you have to do that yourself. And that's procedure number 2. Again, procedure number 2, just use little pieces of pH paper rather than universal indicator. And then you then you write a bunch of acid-base reactions at the end of procedure 2, which is fine. Okay. Procedure 3, I don't think I'm going to say much about that. You're taking some HCl and some acetic acid, and you're adding some NaOH a few drops at a time and measuring the pH. That's kind of interesting. That also is another test of how strong or weak the acids are. Again, I'm not going to say much about that. Leave that to you. Okay, I think we're almost done. Just for argument's sake, I think we did this before. In general, when you mix an acid and a base, you get water plus a salt. I mentioned it before, let's just make sure you understand what's going on. So this reaction here that we did before, it was HCl plus NaOH. Well, we formed water, and I boiled it off, but it's still a product. And then, so H plus and OH minus makes water boiled together. I guess we'd have to call it solid. That's salt. That's just NaCl remaining. It's kind of interesting. So, but it's salt left over from a chemical reaction, not just evaporating salt water. One of the questions, I forget where it is, you can hunt around for it, says, what if I would have done this demo with instead of HCl, I use sulfuric acid and NaOH. What would that white solid be if I did that? So again, I'm going to leave that one up to you. I forget where it is. It's on here somewhere. But you can hunt around for that one and do it yourself. I forget where it is. Sorry. I think that's it, folks. The rest of it are just questions, endo, exothermic, and I think we've covered everything. I didn't talk a lot about strong acids or strong bases to go along with strong acids, but again, that'll be part of your job. So again, to reiterate, see how much of this you can write up ahead of time, and as soon as you come into the lab, just get started with reactions 1 and 2 under redox and go as quickly as you can, and we'll make some game time decisions about getting you the data. I think that's it. So good luck, and we'll see you in lab.